Sorry.
Hi. Thank you. The floor is yours.
Cool. Well, thanks, Peter, for the introduction, and also thanks for organizing and inviting me to take part in this seminar series. It's really a pleasure to be here, at least virtually. So very broadly, my work is concerned with cultural evolutionary questions, and a large focus is on bridging theoretical and empirical research in this field. So I'm interested in understanding whether we can use population level cultural frequency data, so data generated through the occurrence or usage of different cultural traits in a population to learn something about underlying evolutionary mechanisms, in particular processes of social learning that have produced this data. So the guiding question for this talk is, how can we infer processes of social learning from cultural frequency data? But before we go into the how, I want to briefly motivate why this is an interesting or maybe even important question. So our human species has shown an incredible demographic success in occupying virtually every terrestrial habitat on this planet. And by now, it is widely accepted that the behavioral adaptation that explains the success of our species are cultural. They are transmitted among individuals by social learning and have accumulated over generations. So social learning seems to be one of the key ingredients, not the only, but one potential key ingredient of our success. Social learning or cultural transmission, I'm going to use these two terms synonymously, is defined as learning through observations of or interactions with other individuals of the population or its products. Now, so far so good, but there is no single unique way on how we learn socially. In fact, a rather large number of social learning biases or processes have been already found in the literature. So this scheme is taken from a review paper by Luke Randall and all. And all it is supposed to show you the sheer variety of social learning processes that have been identified in human population. So for instance, you can have a conformist bias, meaning you have a preference for high frequency variance in the population, or you can have a prestige bias, meaning you have a preference for variance held by prestigious or influential individual in the population. Or you can have a novelty bias, meaning you have a preference for novel variants, for fashion trends. So giving this large variety of social learning processes, understanding how and when social learning is used is one of the central challenges in cultural evolution. Now, there's already an enormous amount of beautiful empirical, experimental, and theoretical work dedicated to this question, to this challenge. And I won't have time to go into any of this. And today, we're only going to take a slightly different take on this question, because we ask, how can we infer underlying processes from available cultural data? And in many archaeological or anthropological case studies, what we have are population level frequency dealing the usage or current of different variants of cultural variants at one or different points in time. So asking the question the way we have is confronting us with a classical pattern to process or inverse problem. So what we can observe are frequencies, population level frequencies of different variants of a cultural trait, indicated by those different colored dots. But what we actually want to know are the underlying process of social learning that actually produced those empirical patterns. And of course, this question makes only sense if social learning is indeed one of the main causes of frequency change, and that is something that has to be verified upfront for each application separately. So how well or whether at all this inverse problem can be solved depends partly on the quality of the data, but also partly on the quality of the inference procedure. And for that, we advocate the use of a so-called generative inference framework. This framework consists of a generative model and a statistical procedure which provides some information which model outcomes are consistent with the data and which are simply not. So a little bit more detail, the generative model should be designed ideally as a non-equilibrium framework capturing the main cultural and demographic dynamics of the cultural system. But importantly, this model has to produce data that is comparable to the observed data. So in our case, our generative model has to produce frequencies of different cultural variants present in the population, conditioned on a specific process of social learning. So in that sense, we establish a causal relationship between learning process on the one hand and observable frequency pattern on the other. And then statistical comparison in form of machine learning techniques or approximate Bayesian computation then allows for the conclusion about which maybe mixtures of learning processes are consistent with the observable frequency data, and maybe more importantly, which are not. Now, one of the advantages of this framework is the straightforward inclusion of demographic and cultural complexity into the inferential procedure. But of course, this forces us to determine which demographic and cultural processes actually have a sizable impact on the dynamic of the cultural change, and therefore have to be included in the generative model. Because if we omit or if we misspecify the generative model by omitting crucial properties of the cultural system that are able to influence the observable or the observed cultural data, then we might get very misleading inference results. So in this talk, we're going to start to systematically explore the influence of specific demographic and cultural processes on the dynamic of cultural change. And we're trying to understand the implications for frequently used tests of unbiased cultural transmission. So now you might ask, where does now unbiased cultural transmission all of a sudden come from? Because we can't do this exploration in all generality. So for the purposes of this talk, we only consider the scenario that cultural change is determined by unbiased social learning. So we focus on a coarse distinction between unbiased and biased social learning based on data of different temporal resolution. So unbiased social learning occurs when cultural variants are chosen according to their relative frequency in the population, so they are considered neutral with respect to the success of the individual carrying them. So now you might ask, why unbiased social learning? And it's definitely not because we think that it's the most important social learning process, but rather because the field of population genetics has equipped us with an absolute beautiful neutral theory, which provides us with theoretical expectation under very simplistic demographic and cultural assumptions. So in this way, we can quantify the differences in the dynamic of cultural change induced by more complex demographic or cultural assumption by simply measuring deviations from those expectations. So and those theoretical expectations are often generated by the so-called Wright-Fisher model. It's a non-overlapping generation model where a new generation of cultural variants is formed by random sampling with replacement from the previous generation. But just to briefly run through what it means. So it means in each time step, a new generation of variants is formed and the old generation is basically discarded. And this new formation happens by a random copying process. So this variant turns orange with a probability of roughly 3/11. It turns blue with a probability of roughly 6/11, and it turns red with a probability of roughly 2/11. And with a small probability, often called mu, we introduce an entirely new variant to the system that has not been previously seen. So for instance, the composition of the population could look like this. And of course now, we can continue this process and in that way study the temporal dynamic under unbiased transmission as defined by a Wright-Fisher model. So now if we want to see whether our data is consistent with unbiased transmission as modeled by a Wright-Fisher model, we would go through the following steps. First, we would choose an appropriate statistic or maybe summary statistics depending on the available data. Then we would generate its theoretical expectation under unbiased transmission based on the Wright-Fisher model at equilibrium. And then lastly, we would compare the empirical value of statistic to the expectation. But we have seen now that the Wright-Fisher model is, a model of beautiful simplicity. So it assumes that we have non-overlapping generation, that we have non-overlapping generation, well-mixed population with no change in population size over time, and so on. So what if the model used to generate the expectation does not include some of the important features of the cultural system considered? Because most cultural systems we are going to consider won't have any of those features. They are way more complex than that. So, or put differently, can we detect unbiased social learning by using expectation generated by the White-Fisher model if the cultural system generating the observed data exhibits an age structure, exhibits a social structure, allows for learners of packages of traits. So assuming that cultural traits are not transmitted individually or independently, but more as a package with some correlation structure between them. Or if the system is simply not at equilibrium, or if the individuals actually have the capacity of memory. And the list can go further on. These are all projects my group is working on, and in the interest of time, I'm only going to focus on the impact of age structure on neutral dynamics. And this is research I've done with my colleague Laura Fogarty and with Volker Kastrup from the Mertens Institutes in the Netherlands. So, well, what's the influence, or what's age structure doing? So in order to figure this one out, we first have to develop an age structure unbiased transmission model. And that's the sketch of such a model. So first we assume that our individuals, they age in each time step, but they can also die with a certain death probability p death. So in order to keep the population size constant, we assume that in each time step, on average, n times p deaths new individuals entering the system. So and this produces, a population with a nice pyramid-shaped age structure. So, and now we assume that those new individuals, they adopt the variance of a role model that is randomly chosen from a pool of potential role models. And for this pool of role models, we make two extreme assumptions. First, we assume that our new individuals can copy from the whole population. And then we assume that our individuals can only copy from individuals of the recent time step. So only copy from individuals of age 1. So in other words, the process of transmission is still unbiased, is still random copying, but now the transmission process can interact with the age structure of the population. Okay. So in order to broadly replicate archaeological case studies, we assume that we have data in the form of a sample of size n taken from this age structure population at a single point in time. So and now we analyze this sample as it has been frequently done in archaeology by applying the so-called Owen-Watterson test. So in other words, we take our sample from an age structure population and analyze it with an expectation that is produced from a non-age structured population. So just very briefly how the Owen-Watterson's test works. So again, as a data, we have a sample of size n containing k cultural variants that is taken from our age structured population at a single point in time. Now, under the White-Fisher model, we know that a sample of size n containing k variants follows Owen sampling distributions. And that means we can determine the probability that our observed sample could have been generated under unbiased transmission or unbiased social learning. So, and now the test statistic of our Owen-Watterson's test just simply sums the probability of all samples taken from Owen sampling distributions that have a probability that are smaller than the probability of our age structured population. From probability of this from the sample taken from our age structured population. So, and if this tail probability is very small, then we simply reject the hypothesis of unbiased transmission. Okay, so what we do, we run the model, our age structured transmission model to equilibrium and take a sample. Then we calculate the tail probability from the sample. And if this tail probability is smaller than the given critical value, we reject the hypothesis of unbiased social learning. So now we do this many, many times, and now we record the number of times the hypothesis of unbiased social learning has been rejected. Sorry, I Somebody raised their hand.
Yeah, can I ask a question?
Yes, of course.
You mentioned equilibrium.
Yes.
I don't see how this could end up in equilibrium. Can you please elaborate?
So what do you mean? What can
in equilibrium, I would think that there is a stationary distribution, perhaps.
There is a stationary distribution of traits. So, for instance, the number, if you just look at number of variants contained in the population, or even if you were to write down an analytical prediction for the stationary distribution under this age-structured model, that would be assumed. So we have done elaborate checks to know when we precisely reach equilibrium, because the cultural composition of the population at some point is reaching stationarity. Or what gives you a reason to suspect that we never reach equilibrium?
Because new variants can enter and they can exit. So
okay, now I understand the question. So any variant, so no variant will survive indefinitely. So that's every variant that is introduced will die out with probability 1 over time. So in that sense, that is true. However, what reaches stationarity is in some sense the variant abundance distribution. So the distribution of traits of a certain abundance. So those properties of the system, they reach stationarity. However, you're right, no variant will ever go to fixation, because that's just simply not possible. Any variant invented at any point in time will go to extinction. It may take long, but it will happen.
Thank you.
Cool. So yeah, and that actually nicely brings us to this figure. Now let's see what actually happens. At first, we look at the situation where our new individuals can copy from the whole population, and we look at the cultural composition of our population. And this cultural composition is here summarized by the so-called variant abundance distribution. So it records the probability that a variant has a frequency of 1, 2, 3, 4, 5, and so on in the population. So and what we see here, the black lines are variant abundance distribution generated by simulation of a Wright-Fisher model, and the solid orange line is the variant abundance distribution, the theoretical expectation of the variant abundance distribution. And we kind of see nicely that our simulations coincide with our theoretical expectation. So in that sense, stationarity has been reached. So, but what we also see, if you look here at the green, at the purple, and then the blue lines, which you can hardly see, and that shows us the variant abundance distribution for the situation that our new individuals can copy from the whole population, but for different death probabilities. And what we see that they're all overlapping. So in this situation, the age structure has actually no impact on the shape of the variant abundance distribution, at least for the death probabilities we're looking here. Interestingly, we see small deviation between our Wright-Fisher expectation and the variant abundance distribution for our age structured model. But interestingly, this is actually the neutral expectation of the Moran model. So these differences are basically also rooted in the difference between these two different versions of neutrality. So summarizing on the population level, we only see small difference between Wright-Fisher and age structure, but also the age structure population for different death probabilities, they don't seem to show any differences. And these small differences, they don't percolate to the sample level, because this is now the result of Owen Watterson's test. What we see here are the rejection probabilities of samples taken from our age-structured population with these death probabilities for different sample sizes. And we see that for all death probabilities, the rejection probability is roughly about 5%, our chosen critical value. So if our new individuals can copy from the whole population, the age structure had actually no influence on the dynamic of cultural change, or better here, on the composition of the population. But things are very different if we only allow our new individuals to copy from the last time step. So here you see now the variant abundance distribution for a death probability. Green is 0.1, purple is 0.05, and blue is 0.02. And what you see clearly is that first, now the variant abundance distribution are different for different death probabilities, but there is also a stark contrast to the theoretical expectation given by either neutron. So on those differences, they percolate now to the sample level, because now again we see the result of our Owen-Watterson test. And what we see is that for samples of a decent size, the probability that we reject our sample from our age-structured population is increasing. And the higher or the lower p-deaths, the higher or the more severe is this phenomena. If you, for instance, look here, if we have a death rate of 0.02 and a sample of 2,000, then in 85% of the cases, we would reject the sample taken from this population as not being consistent with unbiased transmission. So why is this the case? Well, now in our situation, a large number of individuals, namely everyone larger than one, cannot be copied. So they do not contribute to the cultural dynamic anymore. But they don't go away. They still age and they still persist in the population, and therefore they still, they're still impacting the cultural composition of my population. So it's precisely this accumulation of variants that don't contribute to, or that cannot affect cultural change or cultural dynamic anymore, but are still around, that actually produces the deviation between, our Wright-Fisher expectation and the expectation we get from our age-structured transmission model, where our individuals only can copy from a very restricted copy pool. Okay, so conclude this part. The existence of an age structure does not per se have consequences for our ability to detect unbiased social learning. If, however, the learning process acts on the age structure by restricting the pool of potential role models, the hypothesis of unbiased learning may be wrongly rejected. So, and if frequency data is only available at a single point in time, we require additional knowledge about the age structure and the learning process to achieve accurate inference results. But how can we do this? Well, what we would need is we would need that the probability that a sample of size n containing k variants variant types has been generated by unbiased social learning, and a death probability of a specific size and a specific size of a copy pool. Now, deriving such an elegant formulation like Owen sampling formulation seems analytically very untractable, at least to me. And so that's why we moved to a generative inference framework based on our age-structured transmission model in combination with a machine learning approach to approximate this probability for a situation where we only know that an age structure exists, but we have no idea about the size of the size of the death probability or the size of the copy pool. So our machine learning approach reformulates the neutrality test as a binary classification system. So, and it does this, or to do so, there's a supervised classification system, or supervised classification systems are trained based on pairs of features and corresponding labels. So a bit more precise. So the general idea is that we use our age-structured transmission model and generate a large number of samples of a specific size n. And we generate them under neutral and non-neutral conditions, as well as under different death probabilities and then different sizes of the copy pools. So, and our conditions, neutral and non-neutral, these are going to be our labels. Non-neutral and non-neutral, the labels we're going to infer. So now how do we generate a non-neutral sample? Well, we go back into our age-structured transmission model, and the only thing what we do is we actually change the way we choose our role model. So before we have chosen according to relative frequency, and now we just simply assume a frequency-dependent bias. So if my exponent B is larger than 0, then we have a positive frequency-dependent bias, meaning we have a preference for high-frequency variance. If my B is negative, then we have a preference for low-frequency variance. So these are the two different versions we can model. So, and that of course is also a huge caveat of this approach, because non-neutral is not the entirety of non-neutrality. It is pretty much everything what we include in our training's data pool. So for us, non-neutral at this point means only frequency-dependent transmission. So that's a caveat what you need to always keep in mind when applying these kind of machine learning or generative inference ideas, that basically the labels is what we define in our training data. Okay, so now we have generated a lot of samples where we know whether they are generated under neutral or non-neutral condition, and also we have very substantially the death probabilities and the size of the copy pool. And now we need to, well, classify, we need to summarize those samples. We need to give them features. And those features or summary statistics, they have to be chosen in a way that they allow for optimal or as good as possible distinction between our two labels, neutral and non-neutral. So in our case, we have decided to use so-called Hill numbers. So Hill numbers is a family of diversity measures which approximates the cultural composition of a sample relatively well. So it is a family of measures because we can vary this exponent Q. And with varying this exponent Q, we cannot give less and less and less power to rare variance. So if you have a Q of equal to 0, we have basically just the number of variants, and then we get measures which are can be related to things like the Simpson index or the Shannon entropy and so on. So for each of our sample, we generate such a diversity profile. So a profile of Hill numbers. And now the last thing what we have to do is we have to use machine learning techniques to learn which profiles are indicative of neutral, of the label neutral, and which profiles are indicative on the label non-neutral. So we have to generate a mapping function which does pretty much this classification. And this mapping function is trained on our training data set. And when we have this mapping function, then we can apply any observed sample of the given with the size n. And what we get out is a classification whether based on our model, it is classified as neutral or as non-neutral. Okay, so that's what we're going to do. But before we apply it to our age-structured population, I want to give you a proof of concept that our machine learning approach actually works. So, and here we compare the results of both neutrality tests when applied to data generated by a Wright-Fisher process, so a non-age structured population, but with different strengths of frequency-dependent bias. So in other words, we ask how well do our two neutrality tests or how well are they able to distinguish between unbiased social learning and biased social learning in the form of frequency-dependent social learning, but in a non-age structured population. So let's start with the result of the classical Uhren-Watterson's test first. So we see that on the y-axis we have the rejection probability, and we see that for b equals 0, so if we have actually unbiased transmission, our samples are rejected with roughly 5%, which is all chosen our significance value. So now we see that if our b values deviate from 0, our rejection probabilities increase as it should be. So we see that weak frequency-dependent selection, has only a very weak effect on the cultural composition, and so it's can't really be inferred. However, strong frequency-dependent selection on both ends can relatively safely or accurately inferred from this kind of data, at least if the sample size is of is larger than 100. But what we always interestingly see is that behavior for positive frequency dependence and negative frequency dependence is slightly different. And this is due to the fact that a positive p-value has a stronger effect on the cultural composition than a negative p-value of the same magnitude. So, and the reason for that is the target of those different biases. So positive frequency dependence selects for high frequency variance. And the opposite true is for negative frequency dependence. So in order for negative frequency dependence to become visible, it has to overcome the effect of drift because it has to retain low frequency variance at a higher rate in the population than expected under unbiased transmission. So that's why this asymmetry is actually easily explainable. So, and now what's happening with those guys here? It's a sampling problem. The sample size is simply too small to actually give a to provide a represent sample of the population. So if you take this extreme case here, on average, here we have our negative frequency dependent bias generates, or the sample generated from the negative frequency dependent bias contains roughly 83 variants. So sample size is 100, and this sample contains roughly 83 variants. So, and now what we do is we ask our own Watterson tests, give me neutral configurations of size 100 with 83 variants, and that can only be achieved by an extremely high innovation rate. So, and if we do this, then of course, neutral or unbiased transmission and this negative frequency-dependent transmission are just simply indistinguishable, at least if we have this super small sample size. So, and now if you look to our maximum likelihood approach, we see reassuringly the same U-shape, the same asymmetry, the same pattern. And we see here that we actually also have a little bit of an advantage when it comes to small population size, small sample sizes. And the reason for that is that actually, usually I would say it's a disadvantage that it's not based on a solid theoretical expectation, but in this very particular case, it's an advantage because we are not forcing the samples, or we just basically comparing samples generated by these two different processes. We don't force them to have the same number of variant types. So in some sense, the difference in the number of variants actually provides us with quite valuable inferential information that helps us to make this inference more accurate also for small population sizes. Small sample sizes. Okay, so I hope I could convince you that works. And now we apply our machine learning approach to the same data set as we did our own Watterson tests in the situation where our new individuals can learn only from the previous time step. So, and if you look at these results, again, here the different line are the different projection probabilities for different death rates. It looks like as if our inference accuracy had drastically improved. We are nowhere close to 85%. We are at 20% of misclassification. And we also see that the influence of sample size is not that drastic anymore. So that all sounds good, but this is not the whole story. Because we also ask how good our approach is in actually inferring non-neutral, so frequency-dependent transmission. And here, have a look at this picture. This is where the problem lies. If we have a low death probability, and we can only copy from the last time step, so we have a super deep age structure, and we can only copy from a very limited pool of individuals, then basically my data has no signature about underlying processes, because what we see, almost everything is kind of classified here as neutral. So in some sense, we have to conclude based on this example that if you only have data at one point in time, a sample level data at only one point in time, and we have literally no information of either the death rate or the copy pool from which individuals can copy, then we have a very hard time of actually making accurate inference results. If we have a tiny little bit of knowledge from whom individuals learn, from whom they copy, then you see inference results, they do improve. We get, closer to our U-shape. And even better if we have, a lower p-des rate. But again, if you want to apply it to human populations, this is probably way too high. This is probably also still too high. So in some sense, we have to face the truth that cultural composition of age-structured human population evolving through unbiased transmission may deviate from well-known neutral expectation, such as the variant abundance distribution in specific cases. So analyzing cultural data with statistic or expectations blind to important demographic features of the population can lead to erroneous inference results, as cultural change, so frequency change or parts of the change in the composition of the population caused by those features are wrongly attributed to the learning process. So the generative inference approach allows for a relatively straightforward inclusion of model complexity into the inferential analysis, but the available data may not always be detailed enough to inform on that complexity. So that's the issue what we have seen now. If I have only data on a single point in time, we cannot infer simultaneously the learning process, the death probability, and the interaction with the age structure. So, and that's, that sounds like a very negative result, but I want to stress that I personally feel that this is information, that is helpful information, because we figure out what can we do with what kind of data. So, and that just seems that our aim is to infer, underlying learning processes from data at a single point in time. We have to be careful, especially if I don't know much about age structure and the interaction of age structure with the learning process. And we haven't talked yet about all the other processes I mentioned at the beginning. But on the upshot, what our exercise also gave us, it has shown us that age structure can be ignored when analyzing samples taken at a single point in time, when it is a priori known that individuals choose their role model from the whole population or just simply from a sufficiently large fraction. And I think this is also good news, because in those situations, we know that we don't need to care about this. We don't need to put this detail into our inferential analysis or into our generative model. Or we can also know that Owen Watterson test is just as good. Okay, so I focused a lot on limits to inference based on sparse data. And you might ask, like, okay, that might be true for ecological application, but a lot of modern cultural data sets, they have a much better, especially temporal resolution. So what happens if my data now consists of the cultural composition of maybe a sample of the population at a large number of consecutive time points? So do we have the same problems, or does the situation just simply improve? So, and now, well, we have a lot of data, but that also ask, how do we summarize this data? And here we're going to use very crude summaries. There's probably so much more that can be done, should be done, and we are doing. However, for the time being, what I can present you is we summarize this data by the so-called progeny distribution. And this is a statistics which has been introduced by Alex Bentley into the cultural evolution literature. And this progeny distribution records the abundances of cultural variants which produce k new individuals, progeny, over a fixed period of time. So that's an example of such a progeny distribution. So it's like, it's relatively similar in nature to the variant abundance distribution. So we have here the probability that, or the number of variants with an abundance of 1, with 10, with 100, and so on. So these distributions are usually shown on the log-log scale, and that's what we're going to look at. So now, if you want to, summarize our data with this progeny distribution, so basically we record all the progeny, all the offspring which is generated in each time step, and basically do the distribution over this accumulated, offspring. What we would need is, of course, a neutral expectation, because we would need to know what should we expect this distribution to look like for unbiased transmission in order to have this or to make this coarse distinction whether something conforms to unbiased transmission or simply not. So, and this is something I've done with James Autoir, who is a theoretical ecologist at the University of Illinois. There's another race, Eric.
Yeah, sorry, could you just go back and I wondered what the K matters in what this distribution seemed to be could be well defined without a fixed K. Or...
Okay. No, this is basically so recording the abundance of cultural variants which produce K new individuals. So basically, you can put it in a different way. It says like it gives me the probability that in the time I accumulate my progeny, a variance has accumulated K progeny. So on this K varies from 1, 2, 3, 4, 5 to, I don't know, 10,000. So I will later talk about baby names. So, and there it was the absolute surprising fact to me that there is a huge number of singletons, meaning names that occur only once over, let's say, a 60 period or a period of 60 years. So, and this is what this distribution basically takes into account. So it takes everything what's entering the population in each time step and basically just counts the instances each cultural variant has basically produced in this considered time interval. Okay, so in some sense, the variant abundance distribution describes the diversity of my population at a single point of time. So I would say this is something like the diversity of the census population, whereas this describes the distribution over the accumulation of all offspring basically generated over a specific period of time. So it takes into account kind of the temporal dynamic, because we can also change the time window. But as I said, it's a very crude measure, but nevertheless, I think inference results are much better than I initially thought. There's another hand.
So why is the first the 1 and not 0? I mean, you can have 0 progeny, right?
Yeah, they always count the variant as 1. Sorry, this is a convention. You're right. It could start. There's 2 versions where you count the original variant basically already as a progeny, or where you are saying like, okay, it has to have 1, and then I count all the progeny after that. So, and this is a formulation where we basically take the innovation as already a progeny. So that's basically just a definitional thing, whether you shift the whole thing by 1 or you don't. We have decided we don't shift by 1, so we say like an innovation is also equal a progeny, but that's was just the definition we have made at some point. Okay, so good. So now how do we do this? For the derivation, we didn't use the Wright-Fisher model because the Wright-Fisher model is notoriously difficult for deriving analytical expectation, but we rather resorted to overlapping generation birth death model commonly used in ecology. So the idea here is that the temporal dynamic of the variants are basically generated by reproduction and by competition. So, and the full interacting version of this model could be described by a system of stochastic Lotka-Volterra systems. However, solving for the dynamic of those systems is analytically often untractable. But mean field solutions or mean field approximation have been found to this kind of problems. And those mean field approximations, they take each variant and assume that they only compete against the average state of all other variants. So they don't take into account the specific configuration of abundances of those different other variants at any moment of time. They just let the variants compete against the average other variant. So, and this approximation has been shown to work remarkably well if I have if a certain number of variants are reached. So it doesn't work well if I only have 10 or 20 variants. However, if we are more on the limit to 100 to 1,000 variants, then this approximation almost precise coincides with the results we would get out from the full-blown logical Volterra system. So, and mathematically, this yields to deriving this master equation for the probability that the cultural variance has an abundance n conditioned on its age. So, and that means time since its introduction into the system. So, and this probability, going up and down, is determined by birth and by death processes. So, fantastic thing of this master equation is that it can be solved. It can be solved for t, and with this solution, we actually can derive the neutral progeny distribution. So this gives me the probability that a cultural variant will accumulate k progeny, k offspring, including itself, in the long run, in the long time limit. So this is actually the equilibrium distribution taken over the long time limit. However, you could also write something like this down for shorter periods of time where equilibrium is not necessarily reached. But for our purposes, we use basically the long time limit. And now, interestingly, this progeny distribution has kind of an interesting shape. It consists of a parallel phase with an exponent of 3/2, and then we have an exponential tail off. And this exponential tail off is modulated, or the onset of this exponential tail off is modulated by the innovation rate. The higher the innovation rate, the earlier the onset of the tail off. Okay. So that's cool. And what's even better is that this equation actually only depends on the ratio d/b. So we only have actually a distribution which depends on a single parameter. And that allows us to derive a maximum likelihood estimate for this ratio d/b, which has this simple form. K total is just simply the total number of progeny we have accumulated, and S is just the different number of variant types in this progeny accumulation. So K is the total number of all progeny, and S is, again, the number of different types that is in our progeny accumulation in there. So and that's nice, because now we have a neutral expectation, but we also have a way of how we can apply this neutral expectation to data. So, but before we want to go in there, we need to think about, again, what we wanted to look at, and this is what's the influence of age structure. So, and in order to figure this one out, we again looked at our two extreme scenarios where we have an age-structured neutral model, or age-structured unbiased transmission model, where individuals can only copy or can copy from the whole population, and where they can copy only from the last time step. So shown here at the bottom row. So let's look at the top row first. So here they can copy from the whole population. This is what we have already seen. The variant abundance distribution. We see that different death probabilities do not affect the shape of the variant abundance distribution, and we see exactly the same for the progeny distribution. So we see, the different endpoints are just, it's sheerly due to the model that if I have a higher death rate, I just have more progeny in my system. So, but we see that the shape don't differ for different death probabilities. And we also see that they nicely coincide for our derived expectation, which is the orange dotted line. And we also see again that we have a slight difference to the black lines, which is the expectation under the Wright-Fisher model. Good, so far so good. And now we look at the same, at the situation which gave us a little bit more worries before, where our individuals can copy basically only from the last time step. And here we saw that the variant abundance distribution, well, they changed shape drastically depending on the death probability. But the same is not true anymore for our progeny distribution. We again see that the green and the blue lines, they coincide nicely. But what we also say is that they now coincide with the expectation of the Wright-Fisher model. So that's also not too surprising, because if you see what's now happening is, if you can only copy from the last time step and you only keep the progeny, well, then you have actually a classical White-Fisher model, because now the accumulation effect actually doesn't matter. So that's why it's not surprising that now it coincides with the White-Fisher model. So what we now have is actually something very nice, because what it seems to be the case is that the progeny distribution is actually only very weakly determined or influenced by the age structure and the interaction between age structure and the transmission process. So basically we move only from the black to the orange line. So, and well, that's also an interesting question, because again, the difference between, what I've shown here seems to be just the inherent difference about different versions of neutrality, versions that assume an overlapping generation and versions that assume a non-overlapping generation. And as I told you, deriving the progeny distribution from a White-Fisher perspective is relatively complicated. This does it, but we can only calculate it for a k equal 24, because then, calculating ordered integer partitions is just not possible anymore. So, but already this gives us actually something interesting, because if we compare our the progeny distribution, or the values for the progeny distribution derived by our birth-death process and by our White-Fisher process, what we see is that we actually have the biggest difference in the number of singletons. Afterwards, the differences are actually small, and they get smaller and smaller and smaller. So it's interesting that the difference between these two different versions of neutrality is actually in the frequency of those low frequency variants, in particular in the frequency of those singletons. Then it's like, yeah, okay, what happens if we actually leave those singletons out? And that's what we have done here. This not really should have used different colors, but so black is again our White-Fisher, and gray is our birth-death model. And if we just simply cut off the singletons, they coincide almost perfectly. So what that means for us is that the progeny distribution is only weakly influenced by age structure and the interaction between the age structure and the transmission process. And the progeny distribution can also potentially be a meaningful statistic to analyze the data, because it might be not affected by potentially unknown demographic properties, such as the age structure, at least if we remove singletons. So that's why those progeny distribution, as crude as it appears at the beginning, it might actually, have some use for our inferential purposes. But what we have learned from the statistic is that we can apply this to data which has been generated by or from an age-structured human population, maybe after removing singletons. So that's good knowledge, because then we can use our empirical or our theoretical expectation and our maximum likelihood estimate. And we applied it, sorry, that's what I wanted to say to this slide, can move on. So we applied it to a data set which recorded the baby names for boys and girls in South Australia for a period of 16 years. So the black lines is the empirical progeny distribution given for the girls, and this is the progeny distribution given for the boys. And those gray lines are our neutral maximum likelihood estimate. So what we see pretty obviously is that, well, theory and data actually doesn't match too well. I mean, first of all, we see that there's actually a much, much, much larger number of singletons in my data. So I have many more names which occurred only once than predicted under neutral theory. But also I have quite a number of more names which persist much, much longer, which have accumulated way more progeny than considered under neutrality. This is not to for this talk. However, I want to tell you what this red line is. This is actually progeny distribution generated under what we call a transient anti-novelty bias. So we assumed that new names or new variants coming in have an initial disadvantage of being copied. So kind of the idea, okay, if a name occurs only once, people are suspicious of it. But once this name has been copied a couple of times, so it has been, almost like shown fit for purpose that a child could be named like this, then this disadvantage is decreasing, and then, you almost have your neutral dynamic. And under this transient anti-novelty, we only almost perfectly replicate those empirical patterns. But that's just an aside. But you might have asked, why South Australia? A lot of baby names data, of course, or papers, they of course use the big American databases, which are, by orders of magnitude larger. Well, this was the only data sets which we could find that were complete, basically having the numbers of singletons, names that occurred only twice, 3 times, 4 times. Because many data sets of registered baby names in other regions are incomplete, providing only the most popular names due to privacy consideration. So there are 2 common ways in pre-processing cultural frequency data. So either you remove all names containing less than 5 instances in the considered time interval, we call this total threshold, or you remove all names containing less than 5 instances in each year, we call this year-by-year threshold. And every statistic office kind of uses one of these thresholds, but for whatever reason, 5 is a commonly used threshold for pre-processing this data. So what does it do to our inferential analysis? Well, complete data, here we have what we've seen before, and this is what happens with the total threshold. And that's not too surprising. Remember what we have seen before. What we cut off with the total threshold is actually, we cut off all the rare variants. So we cut off the bit, which kind of was seemingly different between the, between our data and the neutral theory. And now what it looks like that, neutral theory actually replicates the shape of our empirical distribution, and for both the boys and girls relatively well. But if we apply the year-by-year threshold, then something else completely happened, because now neutrality is nowhere near of describing this data. So that was a big surprise. But again, it might not be too surprising if you think of it, because data quality, of course, is an important factor for accurate inference results. Even if we have a lot of data, and I think this baby name data sets are probably the best or one of the best cultural data sources we have at the moment, but we are omitting key parts of the data, such as all low frequency variants. We are not taking that we take a sample from it, maybe cutting off all variants. And this can lead to misleading inference results. But this also points to the potential important role for rare variants for inferential purposes. And for our, what I wanted to show you with this example is that, on the one hand, yes, it is the inference result that needs to be, that needs to be top notch. The inference procedure that needs to be, fit for the task, but also the data needs to have the right quality so that the inference results can act on it. And let me just quickly summarize. I hope I could have convinced you that demographic and cultural properties of the population can have a great influence on the dynamic of cultural change. So we only looked at one demographic property, namely the age structure. However, we have similar results for situations where we have where we assume a social structure between individuals, or where we transmit packages of cultural traits, and so on. Generative inference frameworks allow for straightforward inclusion of demographic and cultural model complexity. And that's fantastic. That's kind of a nice way of trying to include all this cultural realism. But a lot of work has to go into the question of which details really need to go into the generative model. Because even if it is theoretically known what can affect cultural change in the system considered, it's another question if the data is good enough to inform on this complexity. So, knowing everything is good, or knowing what can influence the cultural change is good, but there is no certainty that the data is able to inform such a complex model. And if this is not the case, if the data cannot inform this complexities, then we have to conclude that the available population level data does not carry a strong signature about the underlying evolutionary mechanism. So we cannot make the model more simple, because this is what my this when we have precisely the misspecification problem again. Then cultural change or parts of the composition is attributed to processes that actually were not originally responsible for it. So, and that all sounds a little bit bleak, but this is, at least in my mind, an absolutely rewarding exercise as we learn when we can use population level data to make reliable inference about underlying mechanisms. We have we have population level data much more in abundance than we have individual level data. But we ask much more mechanistic questions. And so this is a kind of a mismatch of the data sources we are having. But knowing what we can learn from what kind of data, I think will, bring especially the field of inference in cultural evolution forward. Okay, with this, I would like to thank my collaborators and you for listening. And I look forward to any questions you might have.
All right, thank you, Anne. The floor is open for discussion.
Alexandros?
Yeah, thanks a lot for the talk. I was wondering, so the process that you showed, like when you copy not from the whole population, but only from one generation before you, for baby names, that might be a bit unlikely. I would think, but let me just to say what I think. Like, there are some strong norms about that, right? So, in Europe, you would probably give the name of your parents to your child, whereas in the US, perhaps you give your own name to your child. Could you be able to tell these differences?
So first of all, the statistics we're having are only on the first name, not on the second name. So it's
Sure. I mean about the first name.
Given no, because you have a lot of people have several first names, and this is, I think, where it's often the granddad or something is included as a second first name. So in our data only look at the first name. That makes sense. So it is a very good question in asking, what does this analysis tell you about the choice of a baby name? And what it does not tell you anything about is the individual motivation about the individual parent on choosing the baby name. This is what this just cannot do, because every parent will have a list of motivation that goes into naming the child. But what we try to pick up is whether they are all of those different motivations, they accumulate on the population level to kind of some detectable force. So for instance, like the anti-novelty bias, that you have seemingly from the data, you have a bias against these singletons. So I was not aware that there are, or at least I was completely shocked on how many children have names that really only occur once in a 60-year period. And, again, the motivation of the parents are, I don't know what they are, but this is also nothing what this research will ever be able to speak to. All what we can is that there seems to be a population level pressure, which seems to be that, okay, once a name has proven it is transmittable, it has been transmitted a couple of times, then this initial advantage seems to fade away, and then they actually behave neutrally. So, and again, this does by no way mean that parents choose baby names in an unbiased way, but it is a remarkable fact. And maybe it's not, remarkable for unbiased for our inferential results, because it actually brings you to the limit of inference in terms of equifinality. But it nevertheless, the pattern that comes out can actually be relatively well replicated by this absolutely coarse transmission biases. So, you know, it has been often postulated that, you know, if we reject neutrality, then you know, we have reasons to believe that there's some directive selective forces in the population. So this is basically the reason why so much an effort also has been put into this coarse distinction between unbiased and biased social learning. But also for that, we have to be very, very careful, because it is precisely this problem of equifinality. So unbiased and biased social learning can produce precisely the same population level patterns. So, and that's actually something where this research on the progeny distribution, well, we start getting at this. And I mean, interestingly, the progeny distribution seems to react very strongly to even very weak transmission bias. But in some sense, if you just have the neutral expectation, that's fine. You can show consistency with neutrality. But what you cannot show is whether it's not also consistent with you know, a whole other set of you know, biased transmission process, because I don't know whether actually their progeny distribution is very different from the neutral progeny distribution. So that's why, you know, equifinality is a huge, you know, cause for pause, especially if when interpreting those analysis results. That's why I always just use, you know, everything what you can do is consistency. Or you have to have very strong reasons to believe that there is, that the distribution with a power law and an exponential tail law is unique. And this I doubt very much. It seems more like, you know, it's an attractor for, you know, a lot of different processes. But so that's why, you know, the question, what it actually tells us is a very good one. And maybe this was a very long-winded answer to, it does not get at individual level processes. It gets at basically aggregated population level transmission biases. So something that all those individual motivation aggregate to. And it's by far, just really because it's important, it's really not saying that any parent behaves in an anti-novel or has an anti-novelty bias. So, and now your question to the baby names, that's actually a pretty cool one, because the reason why I started with the age-structured research was actually because I read in some publication that they were looking at the census data. There is apparently one published census in the US, so basically the variant abundance distribution. And this variant abundance distribution of the names in the US differed insanely from the neutral expectation. It actually showed a power law. And funnily, the exponent was 1.7. So now we're like, what's going on? I mean, it clearly doesn't match. But then we're like, yeah, human population, what we have, I mean, the progeny is an accumulation. So in some sense, it is, they're like, oh, so but does it mean that the age structure then influences all of those dynamics? And then, you know, the whole thing started. But this, if this is correct, and the problem is there's very rare data and basically census name distribution. It seems to be that the census name distribution, sorry, I go. Sorry about this, my computer's a bit slow. No, sorry, now where do I want to go? Okay, sorry, now I'm too far. Sorry, I lost track of what I wanted to show you. So here, if you look at this, the one thing what I didn't tell you is actually that this variant abundance distribution for high enough, for low enough death probability actually has precisely the same shape as a progeny distribution. So if you were to plot, if you were to estimate a power law on these blue lines, we would get an exponent over of 1.5, maybe not precisely 1.5, when we get the exponential tail off. So, and that precisely, this observation actually triggered me, and like, how can we explain that the census distribution of names is so different from what we would actually expect under neutrality? And one explanation, again, is one possible explanation, is that we have such a recency bias. that we actually have, we have a very low death rate for human population. And maybe there is, when we copy, we only copy from maybe not just the last time step, but the last 10 years. So there is this more like this recency in it, that we prefer names which are not, super old. It's one explanation for this curious shape of the variant abundance distribution, which seems to exist in names. So funny that you asked this question, because this was actually, or this observation of this, if you want to call it a recency bias, was actually what made me go into look into the field and say like, okay, what is age structure actually doing? So, and I would say like actually, especially for baby names, a recency bias might be present.
Thanks.
Sorry, somebody else was raised a hand. I just oh here, Matthias.
Sure. So I'm not sure if I'm now going to reveal that I didn't understand anything, but well, let's do it. So when you use the word frequency dependence, my guess was that compared to how it's used in most evolutionary game theory, that I would think that every one of your cases where it is frequency dependent, we would also say it's frequency dependent, but some cases where it's not symmetric. So it seems to me that when you are using it doesn't matter if you would relabel things, just being infrequent has either a disadvantage or an advantage, right? So it's a sort of symmetric frequency dependence in a way.
Yeah, it's still an exchangeable model.
Yeah.
Because it's selection only on frequency and not on the type. So, and I mean, this is precisely what, just for me, apologies, I didn't even think of the game theory distinction. This is, my daily bed and brother, and sometimes I just
Sure.
About it. So this is what we mean by frequency dependence. And this is basically just, for unbiased transmission, you copy relative to relative frequency. So, and what you do with frequency dependence is you distort this relationship slightly.
Yeah.
So you give, a variance with a higher frequency, you increase this probability of copy it at the cost that a variance with low frequency basically had their copy probability reduced. So, and the opposite is true if my B becomes negative. So then we actually provide more, selection strengths, or we just simply increase the probability that the variant is copied that has a low frequency compared to its relative frequency, and we decrease the probability that the high frequency variant is copied. So this is precisely as you said, it's exchangeable. It doesn't depend on the type.
Yeah, so no baby name has an inherent property of being better as a baby name.
Well, I'm not sure being better. It's maybe like it's a baby name. It's like it's on the. Just like people just like or using it better. I mean, it is these baby names go through this very interesting, boom and bust phases where you said like, okay, they're fashion trends for baby names. So this year, I don't know, Emma, Mia, all of those names, they are on the up, and there's Samba, they will be on the down again. You kind of see these boom and bust phases, and so. I mean, if a name is better or not, I don't know. But I mean, what we seem to be able to detect is that the dynamic of the name is in some sense influenced by, in some sense its frequency and its age. So not by the name itself, but just simply by these two factors, by its age and by its frequency. So, and that's basically where this anti-novelty bias was again surprising, because if you have boom and bust phases, you would expect, oh no, there should be a novelty bias selection. But what novelty bias does, it selects against, old variants that are, around for a very long time. And so an anti or a novelty bias can't explain the existence of, I don't know, James, George in English that, persists forever or seem to persist forever at a very high frequency. And so that's, I mean, this is the interesting thing. And that's also the philosophical fact. What is this? Was what we infer? And again, it's not the individual choice. It's basically how the frequency dynamic of the names could be best replicated by. And that seems to be, at least on the example of the progeny distribution, such an anti-novelty bias, transient anti-novelty bias, where initially there's a disadvantage, and once you have once a name has proven useful, that at least a couple of other parents decided, yeah, that's a good one, then this disadvantage has disappeared.
Well, I don't know, but my guess would be that there's also some places where you'll find no cases where there's only one occurrence, because at some places you just can't register a non-existing name, right?
True. I mean, there's all of those convention which does impact those statistics, and of course those conventions have to be taken into account, because otherwise it looks like, oh, there are no singletons, but there are no singletons by definition, because you have to register it. But if baby names are always fun to talk about, and I can tell you what we else did with it. And so with this explanation, or with this discovery that if we threshold data, it actually looks neutral, we thought, like, cool. Now we can actually take a lot of those baby name statistics, because they're all thresholded. We just use the highest threshold used by any of them, and then we have them on the same footing. Then we can apply basically our neutral theory to it. And what we get out is actually an innovation rate. So, it's not the innovation rate, but it's an effective innovation rate. And all data sets are kind of conditioned on the same threshold. So that's actually a cool thing. First of all, was surprising to me that we took data from Western industrial populations. So there is no Asian data set in there. It's basically data from Sweden, France, the Netherlands, Canada, Scotland, the US. So we did it for all of them. And our effective neutral theory, so where we define the cutoff and fit our neutral model, it replicates almost all of them perfectly. So, and that was fantastic, because like, okay, cool. It replicates it super nicely. And what we now have is actually a measure, an effective innovation rate, which we can compare across those systems. And what was coming out was this fabulous relationship that, it was again another scaling relationship. Of course, everything seems to scale, and that the innovation rate scales with population size. And the smaller the innovation rate, the larger the population size. And that was completely unexpected, because that again also is completely counterintuitive with any neutral or even anti-novelty biased approaches, because of course here we treat novelty almost it's dependent on population size in a very loose sense, but having this very strong relationship probably tells you something, that there's some common naming conventions across those countries considered. I don't want to make a bigger claim on this. There's potentially something they have in common, but nevertheless, it was a fun exercise to do. And it was also kind of reassuring that South Australia was not just an outlier, that actually other data set conform to this effective neutral evolution, or a neutral theory where we have a cutoff actually equally well. And that was
we're at time, kind of.
Okay, sorry.
So I have the unfortunate duty of ending the meeting. Nevertheless, we're very grateful for an excellent talk. Thank you very much again. And
thank you very much.
We're going to meet 2 weeks from now.
Okay.
All right. Thank you very much.
Thanks for having me, and thanks for all the questions. It was fun talking about it.
It was definitely fun. Bye bye. See you everyone.
Bye-bye.
Bye.